So going through the version 1 of the 5.3, 5.4 test, you can see that on number 1, the only thing I really did here was rewrite the functions in terms of sine and cosine instead. So I broke cosecant down as 1 over sine. I kept cosine the same because it's already in terms of sine and cosine. And then I rewrote tangent as sine over cosine. Once you do that, you have cosine in the numerator, cosine in the denominator, which cancel, and another sine in the numerator, sine in the denominator, which cancel. A couple concerning things I saw were people writing cosine as 1 over cosine. Cosine is not just equal to its own reciprocal. That wouldn't really make sense. You can't just say 5 is equal to 1/5, for example. So the idea was like cosine and secant are reciprocals, or cosecant to sine are reciprocals. On number 2, I recognized cosecant squared minus 1 as one of the Pythagorean identities on a reference sheet, which let me take those two terms and condense it down to just cotangent squared. And then I rewrote everything in terms of sines and cosines. Now again, cosine squared is already in terms of sines and cosines, so I don't need to do anything to that piece. All I was actually doing was, instead of dividing by cosine over sine, I did keep change flip and multiplied by sine over cosine. That way I have a cosine squared in the numerator, cosine squared in the denominator. All that was left was sine squared. Looking at the reference sheet, when you have pi over 2 minus x, that was equal to sine of x, and sine of negative x was equal to negative sine of x. Now, a lot of people confuse themselves here because they didn't use parentheses around the substitutions they were making, and so they inadvertently changed this multiplication problem into a subtraction problem. But what I'm doing is I'm replacing sine of negative x with negative sine of x, and I'm still multiplying that by the other trig function. So you should have been multiplying these two things together and getting negative sine squared of x. In the case where people did change it to a subtraction problem, I was also concerned that some people said sine of x minus sine of x would equal 1 or would equal negative 1. If you have a number like 5 and you subtract 5 from it, you should have gotten 0 anyways. So that did concern me on a couple papers. Next one, I saw two fractions being added or subtracted together. The strategy I went over for you guys was to get a common denominator. So on the left-hand side, I had to multiply by the right denominator, which is 1 minus sine. And on the right-hand side, I had to multiply by the left denominator, 1 plus sine. That way, each fraction would have a 1 minus sine, 1 plus sine. So when you multiply those together, 1 minus sine times 1 plus sine, those are conjugates. So all you have to worry about is the first and the last product, so 1 minus sine squared. And on top, you're doing 1 times 1 minus sine plus, some people ignored the fact that you're adding these two results together, plus 1 times 1 plus sine. So some people made this into another multiplication problem on top, in which case they distributed in the numerator, which was also incorrect. You are adding these two fractions together. You would have only multiplied the numerators if these two original fractions had been getting multiplied together. So the negative sign and the positive sign canceled out, which left me with just 1 plus 1 is 2. In the denominator, I had one of my Pythagorean identities. 1 minus sine squared is cosine squared. And then I used the reciprocal fact, because we consider it simpler to not have a fraction in your answer. So this is why we use the reciprocal functions. Instead of writing cosine squared in the denominator, I can write secant squared in the numerator. For verifying the identity, you guys did pretty well on number 5. Sine squared plus cosine squared is one of the identities. It adds up to 1. And then 1 over sine of x. Since sine and cosecant are reciprocals, you can just rewrite that as cosecant of x. I did see some people take the route of using sine squared equals 1 minus cosine squared. So they performed the substitution in there, and that's fine. It still worked, because then your negative cosine squared and your positive cosine squared canceled, and you still ended up with 1 over sine of x. So it was an interesting way to approach it. It still worked. Next one on number 6, I took the approach of rewriting everything in terms of sines and cosines. This first piece is already written as sine, so I'm not going to do anything to it. Secant is the reciprocal of cosine. So I'm rewriting it. It's not a sine or a cosine, so I'm rewriting it as 1 over cosine. And then tangent is sine over cosine, but I'm dividing by it, so I decided to flip it as cosine over sine. Now, since this is to the second power, my cosines and sines go to the second power as well. It's like you're doing it twice. Tangent times tangent is cosine over sine times cosine over sine, which gives you cosine squared over sine squared. I have one cosine in the bottom to cancel one of the cosines on top, but there's still one left over. One sine on top to cancel one of the sines in the bottom, but I still have one left over. So there's a cosine over sine, which matches the cotangent function. So instead of writing a fraction with two different trig functions, that's more work that you would have to compute, you can just put cotangent of x. Next, I continued with the changing things to sines and cosines strategy. So cosine of x plus sine of x times sine over cosine. Again, a lot of people kept rewriting things like the cosines and sines in there, but the strategy was to change things to sines and cosines. So if it's already in terms of cosine or sine, you don't need to do anything to it. It's already in a good form for you. All I had to change was tangent, because that is not a sine or a cosine. Once I set that up, I ended up with sine squared over cosine on the right side. So I decided to get a common denominator so that I could add these two fractions together. This fraction has a denominator of cosine, so I had to multiply the fraction on the left by cosine over cosine, which is how I ended up with cosine squared plus sine squared over cosine. Cosine squared plus sine squared is equal to 1 from the Pythagorean identities, and instead of writing 1 over cosine, that's the reciprocal of secant. So now it matches the right-hand side of my formula. This one's a little bit blurry, so hopefully you guys can see it well enough. Secant I rewrote as 1 over cosine, and since this is now a fraction, I took the cosine over here and I multiplied that by cosine over cosine. So now I have 1 over cosine minus cosine squared over cosine, and I'm trying to make it equal to tangent times sine if you can't see that. Well, since this is a common denominator, 1 minus cosine squared is a Pythagorean identity, so I replace that with sine squared. And in the bottom, I just have cosine. You don't actually perform any operations when you combine the fractions. So sine squared over cosine. And then if you group this in a special way, if you think of this as sine times sine over cosine, you can think of one of the sine over cosines as tangent, and then the other sine left over is just staying as it is. So sine squared over cosine can be broken down as tangent times sine. For the solving questions, I saw that these two terms had something in common, so I factored out their common piece, the cosine. So taking cosine out, that leaves me with 2 times sine of x minus 1. I saw a lot of factoring mistakes on this back page, which was concerning. Remember, you should be able to redistribute the cosine back through and come back to what you had originally. So cosine times 2 sine of x would be 2 cosine sine, and cosine of x times negative 1 would be negative cosine of x. A lot of you guys factored in such a way that it would not have redistributed back correctly to give you the original equation. Once I set this up, I set each factor equal to 0 separately. Cosine of x equals 0, and 2 sine of x minus 1 equals 0. The one on the left is already done. For this piece, you would add 1 to the other side of the equal symbol, and then divide by 2. That's where sine of x equals 1/2 comes from. And then when you're looking at your unit circle, you're checking the x coordinates for cosine. That equals 0. That happens in 2 places. And then for sine of x, you're checking the y coordinates on your unit circle and looking for 1/2. So the y coordinates for 1/2 happens in 2 places as well. This one, a lot of people tried to use difference of squares. That is possible. It is doable. But if you're using the difference of squares, the square root of 2 cosine squared of x would be square root of 2 cosine of x. A lot of people just wrote 2 cosine x plus 1, 2 cosine x minus 1. And if you redistributed that, you ended up getting 4 cosine squared in front instead. So you could have used difference of squares, but not many people did that correctly. What I recommended instead, though, was just to perform opposite operations. I added 1 to the other side, divided by 2. So now I have cosine squared equals 1/2. And then to get rid of the exponent, I'm taking the square root of both sides. Many people forgot that when you take the square root of both sides of an equation, you get a plus or minus answer. So a lot of people only got half credit for that. When you take the square root of 1 over 2, that's irrational. Some people just said the square root of 1/2 is 1/2, which also doesn't make sense. Instead, you should have been rationalizing that. Square root of 1 is still 1, square root of 2 is square root of 2. So you multiply top and bottom by root 2, and you end up with this answer instead, which does match what we commonly see on the unit circle. So then I wrote out the angles where I see plus or minus square root of 2 over 2 for the x coordinates. This was another factoring question. My factoring breakdown, you can see that 2 sine of x times sine of x equals 2 sine squared. For the last numbers, 1 times 1 equals 1. And if you're doing the outside and inside product, that would be 2 sine of x plus sine of x, which equals 3 sine of x. When you solve each of those equations separately, you get sine of x equals negative 1/2, because I subtracted 1 divided by 2. And sine of x equals negative 1, so you're just subtracting 1 from both sides. Find the y coordinates equal to negative 1/2. I found 2 of them. And find the y coordinates equal to negative 1. I found 1 of them. On the bonus, these do have a common factor, so I took out tangent of x, which left behind sine squared minus 1. Remember, when you're factoring something out like this using the GCF method, you're essentially dividing the terms by whatever they have in common. So tangent sine squared divided by tangent is sine squared. negative tangent divided by tangent is -1. Some people forgot to put that -1 there. That means I have tangent of x equals 0 and sine squared of x equals +1. When you take the square root of both sides, again, you get the plus or -1 for answers. Now you'll notice I crossed these out because we talked about the fact that if there's a tangent in your original equation, tangent ends up being undefined at the values of pi over 2 and 3 pi over 2. And sure enough, those are the values that popped up. So these are what we called extraneous solutions. You can't use pi over 2 and 3 pi over 2 in the original equation because tangent's undefined for them. However, if you plug in 0 or pi, those answers work just fine. You will end up getting the answer of 0 rather than something undefined. So that's all for the test answer key. If you guys have any questions and you need me to look at your paper in particular, please let me know. This was not an easy test to grade. I did the best I could to be as consistent as possible and give partial credit where I could. If you have reason to think I should look at something again, then just let me know. But some things I did take off a lot of points for were things like not factoring correctly. Those are very important skills for us in this class, and if you didn't factor correctly, it's unlikely that you got many points.